So this video we are again going to derive electromagnetic energy. So electromagnetic energy stored in a pair of inductors with mutual coupling. So I have two coils with say inductance, self-inductance L1, another with self-inductance L2, and the mutual inductance between these two is M, and I have a current I1 flowing here and I2 flowing there. Now this M can have either positive or a negative value depending on so basically what is M? M is say if a unit current flows in this coil, what is the voltage induced in this coil. Now depending on the polarity of voltage that I choose, the voltage may appear to be positive or negative for a chosen direction of current here, and accordingly so accordingly the M will be plus or minus. Okay, now I want to find the total energy stored in this pair of inductors. What I do, I first I'll start with no currents flowing through any of the coils. So initially both the coils have zero currents, and then I slowly increase the current in the first coil until I reach some value I1. At that point I keep the current steady at that value in the first coil, and then I increase the current in the second coil from 0 to I2. Now previously we have seen when we increase the current from 0 to I1 in the first coil, due to the self-inductance, the stored energy will be half L1 I1 square. So let me call this as E1 equals. So this is the energy stored in the electromagnetic form when current is increased from 0 to I1 in the first coil. Now I do the same thing here. I increase the current from 0 to I2 in the second coil. When I do that, two things will happen simultaneously. Firstly, when I'm increasing the current, there will be a voltage generated in this coil which will try to oppose the increment of the current, and therefore I have to do work against that voltage to increase the current. So I have to supply some energy here. At the same time, here also a voltage will be generated because the current here, the flux here links to this coil, and therefore if I increase the current here, that is the flux here, so some voltage will be generated here, and some current is already flowing through it. So the voltage generated here times the current that is flowing there at that point, which is fixed at I1, together will cause some energy to be transferred to it. sorry. But when I energize the first coil, at that time there was some voltage generated, of course, in the second coil, but there was no current, so no energy was associated to that. But now there will be an energy associated to this current flowing in the first coil, and the voltage generated in the first coil due to the increment of current in the second coil. Okay, so I'll have two energies. Let me call E2, which is the energy due to its self-inductance. You can again derive it to be equal to L2 I2 square, or okay, let me do this derivation for you. So at any instant, say the current is incremented from I to I plus di in time dt. Therefore, the voltage generated in the second coil, which opposes this increment, is equal to di dt is the voltage in the second coil, and this times the current I is the power consumed in the second coil, multiplied by time is the energy consumed in the second coil, plus in the first coil there will be also a voltage which is M d let me call it d I2. All of these are I2 because this is the current in the second coil. So now plus M times d dt of I2 is the voltage generated in the first coil times I1 is the power times dt is the energy. Now again note, this energy might actually be negative if M is negative. Okay, so now if I integrate this over time, what I get, so here dt cancels. I am left with I2 I missed L here, very important. I missed L, so I have L times I2 d I2 plus M times d I2, and I1 is constant now, so I can take it out. Now therefore this is equal to, so L integration of I2 di2 is I squared, I2 square by 2 from 0 to I2, plus here I'll have I1 times M times integration of di2 is I2 0 to I2. Okay, so this then turns out to be half L, this is not L, this is L2 according to my notation, L2. Okay, so I have half L2, then I2 square plus here I have M I1 I2. So this is the energy required in the second phase, and the energy required in the first phase was this. So total energy is equal to half L1 I1 square plus half L2 I2 square plus M I1 I2. Okay, good. Now some notes on it. Say both these currents are in a direction so that the flux are additive. So essentially to say that these two are, just the same coil being extended. In that case, M will be positive and will have more energy than these two components. If these two current directions are opposite, I mean the flux is opposite, essentially what can happen, so for example these two coils are identical but the direction of flux is opposite, then when say same current flows through them, essentially there will be no flux at all. The flux in one will be cancelled by the other, so there can't be any electromagnetic energy finally. How do we justify that? See, this quantity is always positive, this quantity is always positive, so in that case this quantity has to be negative, so M has to be negative. Say for example, when L1 equals L2 equals say L, and we also know that, if you recall, M will be in that case for perfect coupling root over L1 L2 is equal to L. In that case, if same current is flowing in two coils, then energy is equal to half L I square plus half L I square minus M, which is equal to L I square. So this is equal to 0. So M can be either positive or negative.